Good morning, students. Yes, hope I am audible and visible for you. Okay, hope you all are doing good. Yes. Okay. Yes, we are now live, and I welcome you all to APJ Academy. Okay, let's get started. So, dear students, this is our full year course. Yes, Protej, good morning. Happy to see you here again. Now these all are the things that you will be getting when you enroll to our full year course. Okay. Now you will get all these courses, all these materials, all these classes just for rupees 490 per month, and that's an enormous discount. And understand, you can crack JEE and NEET with this. With this, just it's a very low pay, right? Okay. If you are watching the class for the first time in the YouTube, please subscribe to our channel, because this channel is going to add value for your preparation. It is going to give you very good content, and that is for free. Okay, right. So dear students, that's all about me. You can read my credentials. Now let's get started. We were discussing about atomic structure. Okay, we already have completed some basic concepts in that we have discussed many important topics. Then we have started atomic structure, where we have discussed about the Bohr atomic model. We discussed about the hydrogen spectrum, the application of Bohr atomic model. Now we are going to discuss about the wave mechanical model of an atom. Okay, and this is also another important topic from this chapter. So here in the wave mechanical model, actually we have to deal with two major concepts. Take some mock test. Okay, we'll consider that. Okay, so in the wave mechanical model, we have two major concepts. First one is De-Broglie concept. The second one is Heisenbergs Uncertainty Principle. Protej is our student, or have you enrolled to our course? Okay, so there are two concepts, that is, one is De-Broglie concept and the other one is Heisenbergs Uncertainty Principle. And in De-Broglie concept is the concept which have explained to us that the matter is having two nature. That is, since the matter is having, actually this concept has evolved from considering that electron is having dual nature. Okay, electron is having dual nature. Since electron is having mass, it shows particle nature, and it moves like a waves. So it shows, we say it shows wave nature as well. Okay, so these two concepts are clubbed together. That is, particle nature as well as wave nature. Particle nature is shown by any particle which has mass, and wave nature is shown by any particle when it moves in a wave form, or when it has lambda, that is wavelength. So that is called as a wave nature. So we know that electron has two nature, that is, it has particle nature as well as it has wave nature. So we know that the fundamental particle of a matter is electron. We know the fundamental particle of a matter is atom, but inside the atom the fundamental is electron, proton and neutron. These are the three fundamentals of atoms. So since electron being the fundamental particle, if it is showing dual nature, then obviously the matter also shows dual nature. So what do you mean by dual nature? Dual nature simply means that it shows both the nature. One is particle nature and the other is wave nature. And that is the concept we are going to deal in this wave mechanical model. The second concept is Heisenbergs Uncertainty Principle. Heisenbergs Uncertainty Principle is a contradictory to Bohr's model. You know, Bohr have clearly explained to us that where the electrons are seen, the position he has clearly located. But according to Heisenberg, Heisenberg told that simultaneously it is impossible to locate the position of electron and to find out the velocity of the electron or the momentum of the electron. So what Heisenberg told is that it is unsure, it is uncertain whether the electron is moving around the nucleus in a circular orbits. That's not a cleared one. That's not a sure concept. Bohr also has failed to explain how he got that the electron revolves in an orbit which have a angular momentum of h by 2 pi, integral multiple of h by 2 pi. He couldn't explain that also. He just gave a value. It will be equivalent to the orbit in which the electron is revolving will be those orbit which have angular momentum equal to an integral multiple of h by 2 pi. That's what Bohr said. But Heisenberg is saying that it is impossible to identify the velocity of an electron and at the same time to identify its position. So without understanding the position, how you are going to know in which orbit it is revolving, whether it's circular, whether it's square, cuboidal, in which orbits it is encircling the nucleus. So this is what Heisenberg told. So Heisenberg's principle is much more clearer than that of Bohr, even though Bohr's cannot be proved true. Okay, so we will discuss these two concepts in detail. Let's start with the dual nature of matter. So in 1924, the French scientist whose name was Louis-De-Broglie suggested that if the nature of light is both that of a particle and of a wave, so he suggested this law or this principle by examining the nature of light. See, we know that the photons have two different natures. One is that of particle nature and the other one, it travels like a wave. So it shows two natures. One is particle nature, the other one is the wave nature. That means the photons or the light have dual nature. And this dual nature should be true for what? For matter also. This is what de Broglie said. Yes, he have discovered or he know that the photons have dual nature. If photons or the light is having dual nature, then obviously the matter should also have dual nature. So according to the particle nature, the energy of a particle can be measured as E is equal to mc square, Einstein's equation. E equal to mc square is the energy of a particle. And energy of a wave is equal to E equal to hc by lambda. So if a matter is having particle as well as wave nature, then the energies will be equal. Both the energy, the particle energy and the wave energy will be equal. If they are showing both, the nature, then the energy should be equal. If it is showing particle nature alone, that means energy of the particle nature is higher than that of the wave nature. If it is showing dual nature, that means both the energy will be equal. So if you equate this mc square equal to hc by lambda, you can cancel c and c square here and you get the value of lambda. What do you mean by lambda? Lambda means the wavelength. The wavelength of the particle. Okay, so wavelength, you get the value as lambda equal to h by mc. So actually c means the velocity of light in vacuum. We are not discussing anything regarding vacuum. We are discussing in different medium. So the velocity of light in medium is considered as v. It is not c. Instead we take it as v. And for your information, the velocity of electron is also closer to the velocity, is almost considered as the velocity of light. Okay, so lambda is equal to, instead of h by mc, we are considering it is traveling in a medium, so we write it as h by mv. So lambda is equal to h by mv. We got the value or we got the formula for finding out the wavelength of a matter. Is that clear? Lambda equal to h by mv, very important formula. Now this is a very important formula which from this many previous year questions you can see. Okay, this is very easy. Just learn this. H by mv, mv means momentum. Mass into velocity will give you linear momentum. So you can replace mv by just p. So h by mv is equal to h by p. Yes, there is a relation between for this momentum as well as kinetic energy, and you can, in the place of momentum, you can write it as root of 2m ke. Ke means kinetic energy. It is kinetic energy. These equations you have to by heart it. Protej, I am from South. I am not well versed in Hindi. That's why I am continuously speaking in English. But I can understand Hindi. But to speak in Hindi is a little bit task for me. Okay. Right. And here h by root of 2mqv, instead of ke is also equal to q into v. Dear students, you have to understand here, q means it is charge. If you are considering an electron, then you can write the kinetic energy is equal to charge of electron is E, that is 1.6 into 10 raised to minus 19 coulomb. So E into V, you can represent it as EV also. Here you could see that this is not velocity, instead it is potential difference. So whenever you are taking charge into consideration, V corresponds to potential difference and it is not velocity. So it is h by root of 2mqv. Okay, so these equations are very important and you can see many questions have asked in the previous years. If you know these equations, that is lambda equal to h by mv equal to h by p equal to h by root of 2mke equal to h by root of 2mqv. Even in the previous JEE mains also, certain questions from this relations have been directly asked. Okay, so here you can see that when a charged particle carrying q coulomb accelerated by applying potential difference V, the kinetic energy is equal to qv joules. That is what we have just explained here. Kinetic energy equal to q into v joules. And see students, by applying the values of the constants, here we know that h is the Planck's constant, which is equal to 6.63 into 10 raised to minus 34. And if you are considering the movement of electron, if the mass of electron, we know that it is 9.1 into 10 raised to minus 31 kilogram, charge of electron 1.6 into 10 raised to minus 19 coulomb. By applying all these values, by substituting all these values, we get the value for the wavelength of electron as lambda equal to root of 150 by V, where V is the potential difference. Remember, V is the potential difference. That much Armstrong we will get. The unit will be in Armstrong, and root 150 equal to 12.27. So you can simplify that. Lambda is equal to 12.27 Armstrong by root V, and this lambda is for the electron. And understand, this is for the electron. Okay, if you are considering any other thing apart from electrons, then you cannot use this formula. Understand, I have written here for electron. Normally it is asked for electron, but if they are asking you regarding any other matter, then you cannot use this formula, that is 150 by V. You have to go for this formula, h by root of 2mqv, or you have to go for this formula. And to select which formula you have to go for, it is with respect to what is given in the question paper. Okay, what all is given in the question paper, with regards to that you have to decide which formula you have to consider. Clear? Now let's see this. De-Broglie hypothesis is applicable only to the macroscopic, is applicable to macroscopic as well as microscopic objects, but it has no physical significance for macroscopic objects. What does that mean? See, if you try to understand De-Broglie with respect to the microscopic, microscopic means those smaller particles which have very minute mass. Okay, And macroscopic particle means you can consider yourself or you can consider any object which can see with your own eyes, which have a considerable mass, is considered to be macroscopic. So here what this note is saying, that it is true that de-Broglie concept is applicable for both the macroscopic as well as microscopic objects, but there is no physical significance for macroscopic objects. You have to understand that there is no physical significance for macroscopic objects. What does that mean? See, you can see here this relation. If the mass is increased, this arrow indicates that the mass is increased. The lambda is decreasing as you increase the mass. If the mass is increasing, then correspondingly the lambda is decreasing. That means for the macroscopic object, the wavelength is very small. Even if I move in a lateral motion or you can say in a translatory motion, if I move, actually my body is vibrating according to de-Broglie's hypothesis. My body is vibrating. But can you see that vibration? No. Why you cannot see that vibration? Because my mass is so high that the wavelength is so small, we cannot identify the vibration or the movement that I have in the wave nature, or my wave nature of my body cannot be physically identified since my mass is so high that the wavelength is so small. So that means there is no physical significance when you consider a macroscopic object. But if you consider a microscopic object, the microscopic object have very low mass, that means the lambda will be very high. So if the lambda is very high, wavelength is very high, you can clearly see the wavelength. You can clearly see the spot, the wave nature of that particle. This is what this note is all about. Hope this is clear. Okay. And also one more thing is that the wave nature of electron was verified experimentally by two scientists known as Davison and Germer by diffraction experiment, not a refraction, by diffraction experiment. By conducting a diffraction experiment, they have verified, these two scientists have verified the wave nature of the electron. Okay. Yes. Now we are moving on to the next topic, that is Bohr theory and de-Broglie concept. Now we are trying to merge both the concept. Okay. So let's start with the Bohr theory. From Bohr theory, we know that the electrons occupy that orbit which have an angular momentum of integral multiple of nh by 2 pi. That means mvr is equal to nh by 2 pi. From this, I write it as r is equal to, or mv is equal to nh by 2 pi r. Let this be equation number 1. Okay. Right. Now, let's consider the second concept, that is the de Broglie concept. De Broglie says that lambda is equal to h by mv. Lambda equal to h by mv. So let me substitute this value of mv here. So what we will get is that h by nh by 2 pi r. So 2 pi r will go to the numerator. So we can cancel this h and h. So we get lambda is equal to 2 pi r by n. That is n lambda is equal to 2 pi r. What does that mean? This is an interesting relation. This means that 2 pi r means what? 2 pi r means the circumference of the orbit. This is the circumference of the orbit in which the electron revolves. So here it is saying that if n is equal to 1, let's say if n is equal to 1, what do you mean by n? N is the number of orbit or the number of shell. So if n is equal to 1, then lambda is equal to 2 pi r. What does that mean? That means 1 lambda means 1 wavelength. Okay, 1 wavelength, or you can say it as 1 wave. Okay, 1 wave will cover the whole circumference of that orbit. That means if an electron is present in the first orbit, then the one wave is enough to cover the whole circumference of that orbit. Okay, what do you mean by one wave? You know that if I consider an orbit, a circular orbit, see the electron is present here. Let me change the color here. So the electron moves like this. Okay, so this is not a good wave. Let me change it. It's a bit confusing wave, right? Okay, we'll draw a good wave. So this is our orbit, and oh, again it went bad. Let me try for the last time. This is the orbit. Yes, almost we got it. Okay, now this is the trough, or we can say the crust or trough, whatever it is. Okay, and the two corresponding or the two succeeding troughs or crust of a wave is measured as one wavelength. This is lambda. Okay, lambda means the corresponding trough or crust of the, it is the distance between the succeeding or the nearest troughs or the crust of waves is called as the one wavelength. So for one orbit, the electron only requires one wave to cover whole of its circumference. If n is equal to 2, that means if the electron is present in the second orbit, then 2 lambda will cover the whole of its radius or whole of its circumference. That is 2 lambda means it requires 2 wavelength. It requires 2 waves. Okay, here it is one wave. Here it requires only 2 wave to cover the total circumference. And if you are considering n equal to 3, that is for third orbit, that means 3 lambda will cover the whole circumference of the third orbit. Okay, so that is a concept regarding Bohr theory and De-Broglie. If you intermix of, or if you connect both the concepts together, you can understand that in the first orbit the electron only have to undergo one wave to cover the whole circumference of that orbit. If you are moving to the second orbit, that means now the radius is much larger, now the circumference is much larger, that means it requires 2 waves in order to complete its orbit. And if you are moving to the third one, then what De-Broglie says is that in order to cover that circumference or that complete circumference of the third orbit, the electron requires 3 waves, that is 3 lambda is required. Okay, is that clear? Now let's move on to the next concept. Okay, here is a question. A body of mass 20 gram and its velocity is given as 500 meter per second. You have to find out the lambda. We know that lambda is equal to h by mv. So h is equal to 6.62 into 10 raised to minus 34. Here mass is given in gram, you have to convert it into kilogram. So that is 20 into 10 raised to minus 3 kilogram into 500 meter per second. Okay, so here 1, 2, 3 zeros, and here I can cancel 10 raised to minus 3, and 2 into 5 is 10. So we will get an answer as 6.62 into 10 raised to minus 35. Okay. So here also 2 into 5 will be equal to 10. So this number divided by 10 means that when 10 goes up, it becomes 10 raised to minus 35. So 6.62 into 10 raised to minus 35 is the answer. Now the next question. Calculate the De-Broglie wavelength of electron present in the third orbit of hydrogen atom. Okay, now let's see for the third orbit. You know the equation that n lambda is equal to 2 pi r. So here it is given as it is third orbit, so we have to find out lambda. So lambda is equal to 2 pi r by 3. Now the only thing is we have to find out the radius of the orbit of the third orbit, right? And we know that Rn is equal to 0.0529 0.529 into n square by z. That is equal to 0.529. What is n square? N square means 3 square, that is 9. Z is equal to 1 since it is hydrogen. So just give the apply the value here. Lambda equal to 2 pi into 0.529 into 9 divided by 3. You can cancel this 9 and 3. You will get 3 here. So you will be getting 6 pi into 0.529. If you calculate, if you multiply it, you will be getting a value nearly equal to 9.96 Armstrong. That is nearly equal to 10 Armstrong. So that's the answer. Okay, hope this is clear. It's a very easy question. So it is easy only when you know the relationship between the Bohr and the De-Broglie concepts. Okay, and lambda equal to 2 pi r. Right? Now let's move on to the next one. This is a most typical question that is favorably asked in the examinations. Okay, you see here two particles A and B are in motion. So lambda A is given, lambda A equal to 4 into 10 raised to minus 5 meter. Mass of B, okay, mass of B equal to 25% mass of A. Okay, 25% means 25 by 100 mass A. That means mass of B equal to MA by 4, because 25 by 100 is 1 by 4. Now velocity of B is 50% velocity of A, that is 50 by 100 velocity of A, that is VA by 2. Velocity of B equal to VA by 2. Now we know that lambda is equal to H by MV. Now let's solve it. Lambda A equal to H by MA VA, and I am dividing it with lambda B because I have to find out what lambda B is, and lambda B equal to H by, instead of writing MB VB, let's apply this value 25, that is MB is equal to MA by 4 and VB equal to VA by 2. This is MB by 4 and it is VB by 2. Sorry, MA by 4 and VA by 2. So we can cancel this MAVA here, and we can cancel H and H. So we will be getting lambda A by lambda B equal to 8. 4 into 2, that is 8. Okay. So lambda A equal to lambda B equal to, sorry, it's not 8, it is 1 by 8. Right. It is 1 by 8. So now what is lambda B? Lambda B equal to 8 into lambda A. Lambda A is given in the question, that is 4 into 10 raised to minus 5. So 8 into 4 into 10 raised to minus 5. That means 32 into 10 raised to minus 5. Okay. 32 into 10 raised to minus 5. That much meter is the wavelength of B. Hope this is clear, students. It's an easy question. Now let's move on to the next one. An electron has kinetic energy equal to 2.8 into 10 raised to minus 23 joule. Then find De-Broglie wavelength. So lambda is equal to, the equation you know, that H by root of 2m ke. Kinetic energy is given. H value we know 6.62 into 10 raised to minus 34 divided by 2 root of 2 into mass of electron is 9.1 into 10 raised to minus 31 kilogram into energy is 2.8 into 10 raised to minus 23. Okay. So if you calculate it, you will be getting 6.62 into 10 raised to minus 34 divided by root of 2 into 9.1 into 2.8. You will be getting a value nearly equal to 51, into 10 raised to minus 54. If you take the root, you will get an approximate value, that is root of 49 is 7. So you will get an approximate value of root 51 nearly equal to 7 point something. So I am going to take it as 7, and here it is 34, and root of 10 raised to minus 54 is 10 raised to minus 27. Okay, since in the options in chemistry, numerical option, in the numerical problems, the options will have a very large differences. So you can approximate, you can take the near values in calculations. Okay, that's not a problem. Always check that the options are of greater differences. If it is of greater differences, then obviously you can take approximation to reach to the answer. So you can your calculation will be a bit more faster if you do that way. So here you can cancel it and you will be getting 10 raised to minus 7. So almost the value will be equal to 9.27 into 10 raised to minus 8 meter. So that will be the value of lambda. Okay, hope this is clear, student. Calculation part is your part. Just try the calculations, do solving it. Because I have lack of time, I am just giving you the answer. Almost I have solved all the steps, only the last step calculation I am skipping it and I am giving it to you. Okay, now let's move on. Hope this is clear, students. Now we are moving on to the next topic. Yes, one more question is there. That is, calculate the wavelength of a moving electron, moving under a potential difference of 1.5. This is an easy question, right? We know that how to calculate the lambda. Lambda is equal to, we have studied that 12.27, or you can 12.27 by, just take root 150. That's better because it is 1.5 now. So it is easy to go with root of 150 by V instead of 12.27. Because the value is 1.5, we can cancel that. Okay. So here lambda is equal to root of 150 by potential difference, and here we know that 150 divided by 1.5, that means we get an answer of root 100. That means lambda equal to 10 Armstrong. I have already told, if you are using this formula, you will be getting the value in Armstrong. So that's an easy one. Okay, now let's move on to the next concept. See, the next concept is all about Heisenbergs Uncertainty Principle. What Heisenberg told is that it is clearly written in your slide that it is impossible to measure simultaneously the exact position and momentum of a microscopic particle. See, you cannot simultaneously locate the position at the same time you can measure the velocity. No, that is not possible. See, without knowing the position, how can you measure the velocity? That's not possible. So that means the velocity of an electron as well as the position of an electron cannot be determined simultaneously. So that's what Heisenberg is telling, and Heisenberg is clearly pointing out that what Bohr said about the orbits, that the electron is encircling the nucleus in a particular orbit, means Bohr is clearly showing us the path or where the electron is present. Okay, and Heisenberg is telling you cannot predict that path. You cannot predict where the electron is. You cannot say that. If you are saying that the electron is revolving in this particular path, that means you are at the same time you are measuring the velocity as well as the position of the electron. Okay, because we know that the centrifugal force and the nuclear force of attraction are equal. From there we started the derivation. So in order to calculate the centrifugal force, we must know the velocity of the electron. Okay, then only we can measure the radius. So the very base of the Bohr concept of orbit, or Bohr concept of orbit is there, that's not a wrong fact, but what he said is that there are certain orbits or there are certain positions or the circuit through which the electron is revolving. So he has geometrically given the shape of that orbit that it's a circular path. What Heisenberg is telling, that is not possible. Yes, electron is revolving in certain orbits, but you cannot say it's a circular path, because what Heisenberg is saying is that electron is moving with such a drastic velocity that you cannot locate its position and find its momentum at the same time. If you can locate its position, then momentum cannot be calculated or its velocity cannot be calculated. That means its direction of motion or its path cannot be determined. If you can determine the velocity, then you have lost the electron. You will, at the very next nanosecond, you cannot spot the electron. This is what Heisenberg told. Okay, so you just understand this much, that it is impossible to measure simultaneously the exact position and momentum. Momentum means actually it is velocity, because we know that momentum is equal to mass into velocity. Mass of an electron is constant. So actually, if I am telling that I cannot measure momentum, that means velocity is constantly changing. That's why we cannot measure momentum. Okay, so momentum equal to mass into velocity. That means simultaneously the exact position, and instead of momentum I can use velocity. So velocity and position cannot be simultaneously measured for a microscopic particle. That's what Heisenberg told. Okay. Now let's look into the mathematical expression of Heisenberg principle. Heisenberg told that delta x, that is the uncertainty in position, into delta p, that is the uncertainty in momentum, is greater than or equal to h by 4 pi. And we know that delta p can be represented as m into delta v, as p is equal to m into v. Mass is constant, so only velocity is the one that is uncertain. So I can write it as delta x dot delta m delta v is greater than or equal to h by 4 pi. I can take this m to RHS and I'll get a new equation, that is delta x in dot delta v greater than or equal to h by 4 pi m. And these two relations are very important, and I'll be giving you one more relation with regards to the Heisenberg principle, that is delta E dot delta T. Delta E is the energy, it is uncertainty in energy, and delta T is the uncertainty in time, that is greater than or equal to h by 4 pi. Equal to h by 4 pi. Hope this is clear, students. Okay, so these three relations you have to by heart it. Delta h dot delta p. Delta x means uncertainty in position. Uncertainty in position. Delta p means uncertainty in momentum. Delta v means uncertainty in velocity. Delta E is uncertainty in energy. And delta T is uncertainty in time. Yes. Okay. Now let's do a problem. So before going into the problem, let me give you a relation, that is, you have to remember this value, that is h by 4 pi. This will be very useful while you solving the numerical problem, and h by 4 pi is equal to 0.527 into 10 raised to minus 34 joule second, and h by 4 pi can be written as 0.527 into 10 raised to minus 27 erg second. So if you by heart this value, then it will be very much easier and simpler for you when you start solving the numerical. So h by 4 pi equal to, this is in joule second is what we normally use. Okay, that's the SI unit. So that's what we normally use. So here the question is about the uncertainty in momentum of a moving electron is 10 raised to minus 15. That means delta P is given, that is it is 10 raised to minus 15. Calculate the uncertainty in position and velocity. So for finding the velocity, we know that uncertainty in velocity, we know that delta P equal to m delta V, right? So m mass of electron we know, so we can find delta V equal to delta P by m, that is 10 raised to minus 15 divided by 9.1 into 10 raised to minus 31. Okay, so that is nearly equal to 1.09 into 10 raised to 15 meter per second. 1.09 into 10 raised to 15 meter per second, that is the uncertainty in velocity. Now you also have to find out what? Calculate the uncertainty in position. So delta x dot delta P greater than or equal to h by 4 pi. So delta x equal to greater than or equal to h by 4 pi, we know that the value is 0.527 into 10 raised to minus 34 divided by delta P given as 10 raised to minus 15. So we get the value equal to 0.527 into 10 raised to minus 10 raised to minus 19, right? So that's the answer. So delta x is in meter. So delta x equal to 0.527 into 10 raised to minus 19 meter, and delta V equal to 1.09 into 10 raised to 15 meter per second. Yes, is that clear, students? Rotage, is it clear for you? Now we have another question. Let's move on to that. Yeah. If the uncertainty in velocity and position is same, then uncertainty in momentum in terms of mass is what you have to find. Okay. Let's see what is given. Uncertainty in velocity and uncertainty in position is same. Both are equal. So we can write the equation delta x into delta P is greater than or equal to h by 4 pi. So here uncertainty in velocity and position is mentioned. So let me take it in that form, delta x into m delta V greater than or equal to h by 4 pi. That means delta x, instead of delta V, I am again writing it as delta x, or we have to find the uncertainty in momentum. So I will apply delta V instead of delta x, because we know that uncertainty in momentum is equal to m delta V, right? So from here we will find out the value of delta V. So delta V into delta V is greater than or equal to h by 4 pi m. That means delta V square is greater than or equal to h by 4 pi m. That means delta V equal to root of h by 4 pi m. Now you have to find out what is delta P. Delta P equal to m into delta V, that is h by 4 pi m. Here I can cancel this, so it will become root m. So I can write it as root of mh by 4 pi. That is the delta P. Hope that is clear, students. Yes. Now let's move on to the next question. Yeah, this is very important question, because this type of question has been repeatedly asked in the many competitive exams. Okay, see here, mass is given. So mass of the particle is given as 10 raised to minus 10 gram, and the velocity is given. Velocity is given as 10 raised to minus 6 centimeter per second. See here, instead of giving the delta V, they have given us the velocity and its measurement, error in the measurement. So we know that percentage error in velocity is equal to delta V by V into 100. If you do not know this relation, then you cannot solve this problem. So percentage error is given as 0.0001, that is equal to delta V, we have to find out, divided by V. What is V? 10 raised to minus 6. Okay, 10 raised to minus 6 into 100. So what is delta V? Delta V is equal to, this is 10 raised to minus 4, 10 raised to minus 4 into 10 raised to minus 6 is 10 raised to minus 10, divided by 10 raised to 2, that is 10 raised to minus 12. So delta V will be equal to 10 raised to minus 12. That much centimeter per second is the velocity. Okay, so we got the uncertainty in velocity. Now uncertainty in position is the formula delta x dot delta V is greater than or equal to h by 4 pi m. We know that h by 4 pi is equal to 0.527 into 10 raised to minus 27 erg. We are considering erg since we are taking the velocity in centimeter per second and also mass in grams. So here we get it as 10 raised to minus 10, that is 10 raised to minus 10 is the mass here, and if you take the velocity to RHS, then it will be 10 raised to into 10 raised to minus 12 delta V. Okay, so by calculating this, you will be getting delta x equal to 5.27 into 10 raised to minus 6 centimeter. Okay, so this is what we will be getting as the final answer. So dear students, today we have discussed about what? About two concepts, or we have discussed about the wave mechanical model of atom, and in which there are two concepts. One is the dual nature of matter, De-Broglie's concept, and the other one is Heisenbergs Uncertainty Principle. Okay, so in the De-Broglie concept we have learned about the wave nature, and we connected the wave nature along with the Bose model or Bose concept of the orbit. Okay, and we got the equation as n lambda is equal to 2 pi r, and the number of waves is corresponds to the circumference of the orbit. And from there we did certain problems, okay, certain numericals. Then we discussed about the Heisenberg Uncertainty Principle, which teaches us that it is impossible for you to find out simultaneously the position and the velocity of or the momentum of a microscopic particle. And also there is a mathematical expression of Heisenberg principle, that is delta h dot delta p is greater than or equal to h by 4 pi, or delta x dot delta v greater than or equal to h by 4 pi m, delta e dot delta t is greater than or equal to h by 4 pi, and we have found out that h by 4 pi is equal to 0.527 into 10 raised to minus 31 or 10 raised to minus 27 erg. Okay, so these relations also we have studied, and also we have done certain numericals, and the last one, which you are now what you are seeing on the screen, is the most important of all the questions we have discussed today. Okay, so that's all students for today's class. Hope you have enjoyed it. Hope everything is clear for you. Now let's meet in the next class. Until then, take care and bye bye. Thank you.